Go ahead.
Okay, so it's our honor to have Avi Loeb here today. We've been most of the time, well, up to now, we've been talking about theoretical aspects of black holes. A moment ago, it seemed we had discovered one, but I guess it has evaporated. And Avi is going to tell us about experimental observational aspects of black holes, which of course is a huge exploding subject now, which could easily fill an entire year course. We're going to have Avi's lecture today, and he's been a pioneer of investigating many astrophysical aspects of black holes and has a very broad knowledge of it, and he's going to give us a broad brush picture of it. And of course, feel free to interrupt him and ask questions. He usually has good answers. So,
thank you, Andy. So first of all, I would like to clarify, is this on, by the way? Okay. Clarify what Andy meant by me being close to observations. It's just that I work in 3+1 dimensions. That's what he... what I would like to describe is what we know in astrophysics about black holes, and feel free to interrupt me, but I also want this to be a dialogue in the sense that I'll describe some topics, many of which I worked on over the past decade, but there are lots of exciting new things that came about recently, and I would like to tailor the discussions to your interests. But I will just start with several general themes, and then we can have a discussion. You will just ask me questions, and I'll elaborate. And the topics that I just wanted to briefly describe to you involve some of the frontiers that astrophysicists are working on. And in fact, on the first one, there should be a press conference within a month and a half showing us the first data of a silhouette of a black hole. So basically a picture, a photograph of a black hole. Why should a black hole have a silhouette? Because if there is glowing gas that emits radiation all around it, the radiation from behind it gets absorbed by the black hole, so you get a dark region behind the black hole. And we'll talk about that. And then, of course, you can imagine, aside from taking a photograph, you can imagine even visiting a black hole. It will take a while because the nearest one, it will take us at least thousands of years, even if we move at the speed of light to reach the nearest black hole. But nevertheless, it could be an interesting trip. And in fact, I think one of the materials that Andy distributed was a recent Scientific American article where I talked about the pleasures of a civilization near a black hole. I mean, there are lots of risks, but you can actually enjoy any experience with nature, and in particular, one with black holes. So if you have additional suggestions for how to enjoy a black hole other than studying about it in a classroom, let me know. I will add it to my top 10. So I'll talk about what happens when you put two black holes next to each other, and a lot of interesting things can happen. One is that there is emission of gravitational waves, and we now, the 2017 Nobel Prize was awarded for the LIGO experiment. When I was roughly your age, I was told by senior astrophysicists that the LIGO experiment makes no sense, that it's a waste of money, and that it will never work. And these were prominent astrophysicists at Princeton, the leaders of the field. And the reason they said that was twofold. One, that they were worried that money will be taken out of astrophysics into this. And the second was that they simply, it was new. I mean, we're talking about using something different than light, a new messenger for signals from the universe, and people resist changes. And on Monday I was asked by the Harvard Gazette what is the one thing that is wrong about the world that you would like to change, and why? And I'm sure each of you will think about something. But my suggestion was to make my colleagues, the tenured professors that I see on a daily basis, kids all over again. In other words, let them be driven by curiosity, let them be open to new ideas, to taking risks, to making mistakes. Because even Einstein made mistakes. Einstein, at the end of the 30s, wrote that black holes do not exist, gravitational waves do not exist, quantum mechanics has this notion of spooky action at a distance that is not correct. He was wrong on all three counts. But that's part of doing science. You can be wrong. Nothing to be ashamed about. It's a learning experience. So anyway, these are just brief remarks at the beginning. But black hole binaries, the fact that they emit gravitational waves, allow us to see the universe in a different way. And you cannot block gravitational waves. And so we can go in environments that otherwise cannot be visible for light. And I'll talk about the consequences of black hole binaries. There is a recoil due to the emission of gravitational waves that has astrophysical implications. And you can even accelerate near binaries. You can accelerate stars to close to the speed of light. So that's a nice environment to actually launch yourself into a journey through the universe. And then stars like the sun can be disrupted when they pass close to a black hole, and we see such events. And finally, I'll mention a few words about primordial black holes. But don't hesitate to interrupt. And the story, of course, starts 104 years ago by now. November 2015, 1915, when Einstein wrote the equations of general relativity, published them in November, and then a few months later, Karl Schwarzschild from the front, the German front of the First World War, he communicated the solution to Einstein's equations that Einstein did not recognize, and that was for a point mass, the black hole solution. And Einstein forwarded the postcard for publication. Unfortunately, Karl suffered a rare lung disease at the front and died a few months later. But he did very important things in astrophysics. He was the director of the Potsdam Observatory, actually, and there are many things called after him, including especially about stars. He died at the age of 40 or so. Okay, so so the thing is, Einstein was a pacifist. He advocated peace. Schwarzschild felt like a patriot. He volunteered for the German military and went to the front. And of course, the difference is that Einstein died at a late age at Princeton and Schwarzschild at a relatively young age. And so the consequence is that if you want to work out the results of a theory for an extended period of time, you're better off being a pacifist. That's just a political statement about if you want to extend your scientific productivity. Anyway, so the Schwarzschild solution has a horizon, as you well know, and you can draw photon orbits. You can launch photons in different directions at any given point. And there is an interesting photon orbit where you can look forward and see your back. And that's a place to put an amusement park, for example, in. And interestingly, so if the emission is situated close enough to the black hole, most of the light rays are absorbed by the black hole, but some can escape. And you can get effects of gravitational lensing where photons are being deflected significantly. So, imaging black holes, the idea is twofold. You can, on the one hand, figure out how gas behaves. It's sort of like water draining down the sink in the vicinity of a black hole. And you can also, in principle, test the general relativity, because there are some suggestions that maybe black holes are modified on scales that we can see in astrophysics. By the way, speaking about that, so what are the black holes that we have in astrophysics? What are the typical masses? Does anyone know? Okay, so black holes in principle can be at any given mass, but in astrophysics you can make them two ways. One is you have a massive star, and the star consumes its nuclear fuel. So a star, you can think of a star basically as a nuclear reactor that is held together by gravity. That's all. It's a nuclear reactor. So it has some nuclear fuel, burns it up, dies. So then when the core loses its nuclear fuel, once it burns the hydrogen into helium and heavier elements, eventually it reaches iron. You cannot burn iron anymore by fusion. You are done. No more fusion. The core collapses. The iron core collapses. So if the star is massive enough, the collapse can only end up as a black hole. If the star is not too massive, it can make a neutron star. So somewhere between 8 and 20 solar masses ends up in a neutron star, and above that in a black hole. But actually it's more complicated. That's one way to make black holes. And if you have very massive stars, maybe hundreds of solar masses, you can reach black holes of 40 or 100 solar masses like the ones that LIGO detected. Okay, then there is the channel of making black holes at the centers of galaxies. So a galaxy is just a collection of stars. Think of it as a collection of nuclear reactors held together by gravity. Gravity seems to be the only long-range force that keeps the universe together, so to speak. So you have these stars, and the stars were made out of gas. So before the stars were made, the gas potentially can just end up, a small fraction of the gas can end up at the center of the galaxy and create a very massive gas cloud. And that gas cloud can collapse to a black hole. So you start from a seed black hole that can be much more massive than a single star, and then it grows by accretion of more. And this is called an active galactic nucleus, where gas is feeding the black hole. And we can then see the radiation coming out. Because as the gas falls onto the black hole, it heats up and it shines very brightly. The energy comes from viscosity. The angular momentum, the rotation, has to be dissipated. So just like, by the way, did you ever think about how the water drains down the sink? I mean, in principle, it could have gone forever. The only reason it drains is because there is viscosity. So it heats up. Some of the rotation energy is dissipated into the water, and then the water heats up a little bit, but still falls into the sink. And you can think of a black hole as a sink. And angular momentum is dissipated, and then the gas collects at the center. Okay, but in the meantime, the gas heats up to a high temperature, and you see it very bright. And we call these objects quasars, or active galactic nuclei. They're very bright, and sometimes part of the gas, instead of falling into the black hole, gets channeled into a jet in about a tenth of all cases. So we can study the way gas behaves, and we can also test general relativity.
How sure are we that those are the only two ways that black holes get made?
No. So then there is a third way. Thank you for the question. The third way is if in the early universe you have a perturbation where the density increases above the critical density significantly on the scale of the horizon of the universe. Okay? So in the standard cosmological model, perturbations are produced during inflation, let's say, and they're always of the order of 10 to the minus 5 when they exit the horizon, because that's a very low level of fluctuations we see today. And that's true throughout inflation. You always have 10 minus 5. Now, when they enter back into the horizon, they're always very small. But if you had a phase transition in the early universe that generated density fluctuations of order unity somehow on the scale of the horizon, then you can think of it as a region of space where gravity is stronger than, where the gravitational binding is stronger than the expansion, kinetic energy, so that it's just like a closed universe that ends up in a big crunch. Okay, so So if on the scale of the horizon you have density above the critical density, that region collapses and it collapses to a black hole. And that is called the primordial black hole. And to get that to work, you need a density fluctuation of order unity on the scale of the horizon. So if you just rely on inflation, the probability for that is tiny because it's the probability distribution of density fluctuations is Gaussian. And if the variance is of order 10⁻⁵, you need to go to the tail of the Gaussian by a factor of 10 to the 5, okay? And e to the minus 10 to the power 10 is completely negative. So you have no primordial black holes if you take Gaussian fluctuations. But you can have non-Gaussianity, or you can have phase transitions that will generate that. And then you can get primordial black holes. Now, in principle, it's an open game. You can get primordial black holes on any mass scale you want. Those that are very light, less than the mass of an asteroid, roughly 10 to the 15 grams, will Hawking evaporate during the age of the universe. So the evaporation time equals the age of the universe for 10 to the 15 grams, okay, today. And then if they are less massive, they would evaporate in the past, or we will not have them. But if they are more massive than 10 to 15 grams, they can serve as the dark matter. So that's an attractive possibility that is by now ruled out, actually based on all kinds of constraints. But it's still possible that it could be a small subcomponent in the dark matter, less than 10%, less than 1% at different masses. The constraints are different at different masses. So primordial black holes are the third channel.
So what's the window of masses that's astrophysically allowed?
No, so astrophysically all of them are allowed as long as they have a negligible abundance relative to the dark matter. Relative to the dark. So you can't make the dark matter out of any primordial mass black hole. In principle, you can think of a fourth channel, which is an advanced enough civilization that makes a black hole on its, it's possible.
What would those be?
Well, it depends how you do it. If you make it through a collider, it could be tiny, right? But if you make it through some huge engineering project, for example, the average density of a 10 to the 8 solar mass black hole is the density of water. I mean, if you take the mass divided by the Schwarzschild volume. So you can think of an engineering project where you pour enough water in the orbit of Jupiter, make a 10 to the 8 solar mass black hole. Yes?
Would it be dangerous to have small black holes, like say one that could fit in this room? Because if we keep tossing stuff into it, then maybe it could grow and eat the Earth.
Okay, so this is an excellent question. So there is actually a paper on that. Pretorius was part of that. So the question was, suppose there are primordial black holes, can we detect them if they pass through the Earth? Okay, that's a practical question. And the answer, it's really difficult because they have, so an asteroid mass black hole has a Schwarzschild radius, which is, and I'm talking 10 to the 15 grams, so like a kilometer size kind of asteroid, has that mass. So think about a kilometer size rock, the mass of that being in a black hole, it means that the Schwarzschild radius is the size of a proton, basically. Okay? That's the Schwarzschild radius, size of a proton. Now, such a black hole passing through your body will just go surgically through it. I mean, of course, gravitationally, things will get attracted to it, but not much. I mean, an asteroid of a kilometer is not affecting. So what it could do is, when it goes through a proton, it has the size of a proton, the gravitational force, I don't know, it will not do much, basically. But if it passes through the Earth, and by the way, such a black hole emits Hawking radiation at a very high temperature, of course. But if it passes through the Earth, it would basically create seismic noise. And that was the paper. The paper was, what kind of seismic noise would you get? And could you detect it? And the answer is not, it's very challenging. I can direct you to that paper if you want. But
there's some threshold where it does become detectable.
Yeah,
obviously.
yeah, definitely. But then you have to ask, if you increase the mass of the black hole, you reduce the number density of such black holes, because the total mass density is limited. So then it becomes rare for them to come close enough. And I will talk about primordial black holes towards the end and the constraints we can put on them. Okay, so let me move on. So basically, I mean, you can see here the movie. We see stars moving around the black hole at the center of the Milky Way galaxy. It's called Sagittarius A star, and it's just a name because this was a radio source for many years. People didn't know what it is. It didn't move. It looked like a very massive thing at the center of the galaxy. It turns out that this Sagittarius A star, this radio source, is a 4 million solar masses black hole at a distance of about 24,000 light years. So what we see now from it...
Wait, is it the bright dot, the black hole?
Yeah, the thing that doesn't move. And by the way, you saw this gas stream. That was a simulation of... We do see streams of gas. We don't understand where they come from still. And they're probably produced by something being torn apart in the vicinity of the black hole. But the important thing about Sagittarius A star is that it's the largest black hole on the sky. So if you wanted to take an image of a black hole, you would look for the biggest one on the sky, right? I mean, it doesn't mean that it's the biggest one in its own frame of reference, you know, like it's the most massive black hole, but it needs to be close to us and yet massive. And so all the stellar mass black holes are much tinier than this one, and Sagittarius A star would be the first target you want to look at if you have limited resolution. And by the way, the gravitational acceleration on the surface of, at the horizon of the black hole is 500,000 g. So just to give you a sense, a pilot, pilots go on an airplane and, it's really frightening, but they can get up to 10 g or something, and it's really dangerous. Okay, let me ask you a question. Is it dangerous to come close to Sagittarius A star where there is an acceleration of 1,000,000 g? What do you think? Those who think it's dangerous, please raise your hands. Okay, you are wrong. Why? And this is something that Einstein recognized. Einstein had this thought experiment. You are all familiar with it. If you go to an elevator and someone cuts the wire that holds the elevator and the elevator freely falls, you see that in movies, right? And you are in the elevator. Think about it. I don't want you to lose sleep tonight, but still, it feels as if there is no gravity, right? Because the elevator falls exactly at the same rate as your legs. So there is nothing to push against your legs. So if you are freely falling in a gravitational field, it's as if there is no gravity. Okay? And that led Einstein to the equivalence principle, the idea that, maybe it's space and time. It's something that, gravity is not really a force. And so the point is that if you have 1,000,000 g, who cares? As long as your entire body feels the 1,000,000 g, you will not feel gravity. You can go through the horizon without nothing happening to you. Okay, so just acceleration is not an issue, yes?
So, right, so when you feel like you're in free fall, but whenever we talk about this elevator experiment, the statement is very local, so because you still get tidal forces, right?
That's the point. Wait, you ruined my punchline.
Okay.
Yes. Well, first let me go through an intermediate step. What happens to a pilot when he or she goes faster than or with an acceleration more than 10 g? Why is the body feeling bad? Well, the point is it's not a uniform acceleration, right, for the pilot. If it was uniform acceleration, no problem whatsoever. By the way, just to give you an anecdote, 1 g over 1 year times 1 year, what speed is that? Speed of light. Now, this is a complete coincidence. That is, when I did the calculation first, I was really struck. It's amazing. So if you accelerate at 1 g, like if you go on a spacecraft and it feels just like being on Earth because the spacecraft is accelerating at 1 g, you wouldn't feel any difference compared to Earth. We can have this class on the spacecraft, 1 g. Perfectly comfortable. You do it for 1 year, you reach the speed of light. You do it for 20 years, you reach the edge of the universe, which is 10 billion light years away. But time is ticking much more slowly in your frame. No problem. We can reach the edge of the universe if we had a spacecraft that keeps accelerating us for 20 years at 1G.
How long does it take to get 90% light speed at 1G?
90% of a year. So it's not much.
You never get to the speed of light. Right?
That's right. You never. So you increase your Lorentz factor. It requires a huge amount of energy. That I didn't touch the engineering aspect of this, but the physics aspect is that if you accelerate at 1G and you feel comfortable for 20 years, you reach the edge of the universe. That's a remarkable fact. You always think of yourself as never being able to go across the universe, right? Because it takes much more than your lifetime. But that's not true if you accelerate. Okay, so 1,000,000 G is no problem as long as it acts on your body uniformly. The problem is tidal, the tidal force, which means that Einstein's equations tell you that what matters is curvature, the curvature of space and time. What is curvature? The curvature is related to the tidal force. So the curvature is the only thing that you can measure locally related. So in this elevator, falling elevator, if there is a tidal force, if there is a difference between the top of the elevator and the bottom of the elevator in the gravitational force, you can measure that. You can do an experiment that measures that. But of course, that difference diminishes as the size of the elevator goes to 0. So locally, you can never do. But in principle, the curvature of space and time, which relates to the tidal force, is what you can is a physical thing. Okay, what does the curvature do? What does the tidal force do? Well, it basically stretches your leg faster than your head. That doesn't feel comfortable, right? So fortunately, that is not an issue with Sagittarius A star. The tidal force will rip our bodies if we get close to the singularity, very close to the center, but at the horizon, we wouldn't feel anything. It's something to keep in mind if you contemplate going there. But there are several orbits. There is the Photon orbit. There is the innermost stable circular orbit, where if you go there, then that's the last orbit where you can circle around in a stable fashion. And that's important for gas, because it means that when gas gets inside this orbit, it falls in. It cannot continue to go around. It doesn't need viscosity, it just falls in. And so that's the innermost orbit where you find gas, and that's where you get most of the radiation from as a result of viscosity. Inside of this orbit, there is not much time to emit radiation. And another significant fact about this orbit is when you calculate gravitational waves, for example, for LIGO, if you have a binary, the waves are emitted until the two black holes reach roughly the innermost circular orbit, and at that point they plunge into each other, and you don't get as much radiation. So you get much more radiation until the last orbit. And there is this, that's an old commercial. You probably were not born when this commercial was on TV by Verizon. This guy was going around with a cell phone and asking, "Can you hear me now?" Oh, you were alive, okay. So you can imagine this guy. So we made this plot for Scientific American, and they really liked it until the editor realized that this guy is her brother. And then, so we didn't put it in the in the final article. But anyway, so you can imagine putting this guy near a black hole and seeing, eventually as he gets close to the horizon, he will get redshifted. And it will take a very long time for us to hear what he says. Eventually, we will, beyond a certain point in time, we won't be able to hear anything, because he already, in his own rest frame, crossed the horizon at that time. Okay, so suppose you have a hotspot. Here is a thought experiment. Suppose you have a flashlight moving around the black hole. What would you see? One can calculate that, and we did that with Avery Broderick about 13 years ago. And back then, before we wrote this paper, this is just an important lesson for you to learn, that don't listen to what other people say. If you want to do some calculation, just do it. Because on this thing, basically I was on sabbatical at Princeton, and some people came, and I said, let's calculate what happens to a hotspot and how would it look like. And all the experts basically said, oh, don't bother, because the environment of a black hole is turbulent. There would never be a hotspot moving around. And I was thinking, just because the sun has these hotspots, that you can imagine a reconnection event, a flare, that would move around. Anyway, we did the calculation. We didn't pay attention. And Avery Broderick was a postdoc that just arrived here, and he just did what I asked him. And he was, and he had all the tools to do this. And so then 14 years later, there is a press release from Garking from an instrument called Gravity, where they actually saw the centroid of light of Sagittarius A star is performing a circle on the sky. So it's the first instrument that can actually monitor the motion of the center of light. And 5 months ago, they reported the results where they see that it goes in a circle, which resembles this prediction of a hotspot. So
It's a hotspot on what?
it's a hotspot in the accretion disk around the black hole. We don't know what it is. It could be, the most likely, just like the sun has flares, you have magnetic fields that cut through each other, and then magnetic field lines basically go through reconnections. So topologically, when two magnetic field lines cross, they need to somehow pinch off. And that is happening in reality on the sun when the resistivity of the plasma starts to play a role, when the electrons. So what happens is you get some dissipation of magnetic energy, and the field changes its topology from being a cross topology to being two things that pinch off. And that's called the reconnection event, and you get a lot of energy released. We see it on the sun, the flares. And the same thing can happen in an accretion disk. And the only question is, why does it survive half an orbit or a full orbit? The criticism we had 15 years ago was, you would never get something to survive a significant fraction of time. You will just get fluctuations. But in reality, they see this motion of the centroid of light, which it's a great triumph of observational astronomy to actually reach that point where you can see the motion. But at the same... Sorry?
What's the radius of this motion?
So 7 gm over c squared, roughly the innermost stable circular orbit, which is 6. So it's 7 plus or minus 2. It's consistent with 6 for a non-spinning black hole, just next to the last stable orbit. And they have some constraint on the spin, but more likely low spin black hole. So that's amazing. That is before the Event Horizon Telescope comes with this image that I'm trying to describe here. So this is from a Scientific American article a decade ago that we wrote. If you have a bright spot, there would be several effects that play a role. One is gravitational lensing, where you can get multiple light rays going around the black hole and being observed. You also get the Doppler effect, when the material that is approaching us emits more brightly because of the beaming, relativistic beaming, whereas the material that runs away from us is more dim. It's running away from us, and it's less bright. And so as a result, you end up with this crescent, moon crescent shape. And there is a secondary image. And it depends on the inclination. So here we show different inclinations, different spins, as to what you see. You see the image, in principle, if you analyze the image, you can tell the inclination, you can tell the spin, and the mass of the black hole. And the scale that we are talking about is of all the tenths of micro arc seconds. This is the silhouette, the shadow, and it has roughly the scale of the radius of 5 gm over c squared. But this, an amateur astronomer telescope that you can buy for a few $100s would reach arc second resolution, a few arc seconds. Here we are talking about a factor of 100,000 smaller angular scales. So can anyone, well, actually we'll get to that. So let's, well, these are standard things that I assume that you heard about, how the innermost stable circular orbit depends on spin. This is the spin parameter going from maximum co-rotating orbit to a counter-rotating orbit. And you see the ISCO, the innermost stable circular orbit, in units of the Schwarzschild radius here. And then there is the horizon, which approaches half of the Schwarzschild radius for a maximally spinning black hole. And then the radiative efficiency is simply the energy, the fraction of the rest mass that is converted to radiation, which depends on the radius of the ISCO. It's basically the gravitational binding energy at the ISCO. And of course, it gets to very high values for maximally spinning black holes, 42%. So if you throw your trash near a rapidly spinning black hole, you can get 42% of the rest mass of this trash back in the form of clean energy. I don't think there is any other engine that can do it for you. So it's quite remarkable, and maybe some of the light that we see from black holes are trash thrown in by nearby civilizations. Well, there are some simulations of how the turbulence operates. Again, we cannot trust this simulation. Some people have this notion that if they put things on the computer with a lot of, and use the very best supercomputers, they get better understanding of physics. I don't share that enthusiasm. I think, many times what you put in is what you get out, and if you miss something, you don't get it. And many other times you just get something, but it's just like being an experimentalist. You get something, it doesn't improve your understanding. You just know that you put something in, you got something out, but it doesn't mean that you understand why you got this something out. So, but on the other hand, there are other astronomers which are much more enthusiastic, like the old generation. Martin Rees is, every time you show him a simulation, he says, "Whoa, that's amazing!" And but I don't share that enthusiasm. Anyway, so there are three fortunate coincidences about Sagittarius A star. One is that the accretion flow, the gas that falls into it right now, is very dilute. And we are lucky that not much gas is feeding Sagittarius A star because we can see through it. Okay? And there is, at wavelengths that are shorter than 1 millimeter, the gas is transparent. That's one interesting coincidence. At wavelengths longer than 1 millimeter, the gas is opaque because of synchrotron self-absorption, so you basically cannot see all the way through. You see some extended blurred image. Then there is scattering in the interstellar medium, which means that the gas between us and Sagittarius A star is not uniform. It has inhomogeneities. And you get effects of lensing because of, just refractive index changing. And that blurs the image. But again, at 1 millimeter, it doesn't really blur the image. So wavelengths shorter than 1 millimeter, again, we can see through the gas in the interstellar medium. A coincidence. The transition is around a millimeter. And then the final coincidence is you ask, okay, suppose you have a telescope. The biggest telescope we can imagine is the size of the Earth, right? So what should be the wavelength such that we will resolve 50 microarc second, resolve the horizon? So in optics, a resolution of a telescope or anything like the lenses in your glasses and so forth, it's the wavelength over the diameter. Okay, that's the angular resolution, the wavelength over the diameter. And you must have learned that. I don't know if in high school or in your bachelor's studies. But at any event, if you take the size of the Earth and you ask what wavelength do we need to use such that we will resolve Sagittarius A star, the answer is 1 millimeter. 1 millimeter over the diameter of the Earth gives you a resolution good enough to see the shadow. Coincidence, Mother Nature was very kind to us. 1 millimeter works on all three counts.
Would it have been just as kind for Mother Nature to do 1 millimeter, 10 millimeters, 100 millimeters, and still 1 millimeter.
Sure. Sure. I agree. But it could have been much worse, let me put it this way. So we should always look at the full part of the glass, you know. And by the way, this gives a purpose for the life of some experimentalists around here, like Shep Dolman, who is the director of the Event Horizon Telescope. That's what he does for a living. The fact that these coincidences exist gives him a reason to wake up in the morning, actually.
Are we viewing the accretion disk edge on? The accretion disk of Sagittarius A?
That's something that was only constrained recently by this hotspot observation, and they claim that it's within 30 degrees of face on. Otherwise, we didn't have any constraints. But if we get the image of Sagittarius A star with the Event Horizon Telescope, we will. Now, I should warn you that in a month and a half, they will not talk about Sagittarius A star, probably. They will talk about another black hole. Anyway, these are the synthetic images that you get by trying to figure out, you know, what you should expect from an accretion disk around Sagittarius A star at different frequencies, with and without interstellar scattering. And you know, the idea is, how do you build a telescope as big as the Earth? Well, you use interferometry. So you basically put stations. You put observatories in different places. You notice that the observatories are always on land, right? You cannot put an observatory in the ocean. That's a limitation. But by the way, it's really fortunate that you know, roughly half of the Earth is land. Did you ever think about that? You shouldn't take it for granted. There are lots of planets out there, and most of them are either covered by water or covered by land. We actually wrote a paper about that, trying to figure out what is the chance that we will be on a planet that has roughly half and half, and how lucky are we? And is this really what's the likelihood of life in other places? You know, that affects the likelihood. At any event, we are lucky. Some of the water froze in the caps and may soon melt because we are misbehaving, you know. But the point is that we can use observatories separated by the diameter of the Earth and get a resolution that is dictated by the wavelength divided by the diameter of the Earth. And we do it by basically recording the signal from Sagittarius A star in real time on each of these, putting the information on tape, and then bringing it to one location and cross-correlating the electromagnetic field. I mean, not just the intensity, we're talking about the amplitude of the field and the phase, okay? And that, by using the phase information, you can do interferometry and just basically get an image. These are some of the observatories. By now, there are more of them incorporated. The very first experiment that was done was with 3 stations. And
One
it
is in the ocean, isn't it?
Yes, Hawaii. Well, it's not really. I mean, what you see as a small piece of land is usually the tip of a mountain. Yeah. In the case of Hawaii, it's basically the volcanic activity that made this island. Yeah. And by the way, the volcanic activity led to Mauna Kea, which is one of these mountains in Hawaii, where there are many telescopes. And it got to the point where the latest telescope that people would like to put there, it's called the 30-meter telescope, there was a lot of protests from the local population because they regard the mountains as sacred. And we are not partners in that telescope, but I was asked to give a public lecture to help convince the local population. And my colleagues here said, "Why would you go there? You are helping our competitors." And I didn't care about it. But it was interesting because I learned that they hired a priest that would check. You know, the priest is full-time employed by the project, would make sure that they don't misbehave with the rocks as they build the telescope. Um,
How do you misbehave with rock?
well, it has to do with the religion that says that the rocks, if you break them inappropriately, or there are some types of rocks that you shouldn't touch, but they can bleed actually. Anyway, moving on. So these three experiments did put some interesting constraints. This is the actual black hole that we can also look at, aside from the galactic center, that you might hear about in a month and a half. It's called M87. It's at the center of a cluster of galaxies 2,000 times farther than Sagittarius A star. And that's the nearest cluster of galaxies to us. It's called the Virgo cluster. M87 is a giant galaxy sitting in the center of that cluster. By the way, why would the giant galaxy sit in the center? And why would the biggest black hole be in the center? The answer is simple. If you make a cluster of galaxies, galaxies near the center collide with each other. Then you start building up a big galaxy there. And it's called the galactic cannibalism, where small galaxies are eaten up by a big one. And through these mergers, you build up the central black hole. And this one is 6 billion times the mass of the sun. I mean, there are bigger black holes by a factor of 2 or 3 in the universe, but it's one of the biggest ones. It's huge. It has a size big. The Schwarzschild radius is bigger than the solar system. It's 1,400 times more massive than Sagittarius A star. And it's roughly 2,000 times farther. So the Schwarzschild radius scales like the mass, and the angular size of the Schwarzschild radius scales like 1 over the distance. So it nearly compensates. So if you have the resolution to image Sagittarius A star, you can do the same in M87. Main difference, there is a jet. So some of the material gets funneled into a relativistic speed. And that's the place where you might want to surf on light sails if you are trying to have fun near a black hole. But you see this tightly collimated jet at different wavelengths. This is in the radio, optical, X-rays. Quite remarkable. And goes distances that are as big as the host galaxy or even bigger. Millions of light years in some cases. And that's, sorry?
I guess the size scales linearly with the mass, but do we have any, what about the energy emission?
The energy, okay, so there is a limit. Maybe I should just mention that because that's really a fundamental issue in the context in astrophysics of black holes. So if you have a black hole, and of course the force of gravity, in the Newtonian regime, as long as you don't get very close, the force of gravity is just related to its mass over the distance squared. But then if there is radiation generated near it, there is a force outwards due to the luminosity emitted. So the luminosity is just the derivative of the energy with respect to time, the power that is emitted. So what happens to this luminosity? Well, if you put an electron has a Thomson cross-section for intercepting the radiation. So you can imagine the electron having a finite cross-section for intercepting the radiation. It's called the Thomson cross-section. This Thomson cross-section times the flux of radiation coming through. So what is the flux? So the flux, let's write it here, of radiation will be the luminosity divided by 4 pi r squared, okay? And that's the energy flux. Then if we want to get the number flux, we divide by the energy of a photon. But the momentum that each photon can deliver to the electron is the energy divided by the speed of light. So altogether, if we want to get the momentum flux, we just divide by the speed of light. So this is the momentum flux. And you take the momentum flux times the cross-section. What is that? What is the momentum flux times an area? So it's momentum flux is how much momentum per unit area per unit time you get. Now when you multiply by area, it's how much momentum per unit time. That is called force, right? Momentum per unit time. That's how much force is acting on the electron. Now for every electron on which this force acts, oops, why did I put this? On which this force acts, there is a gravitational force acting on a proton. So this is the attractive force on a proton. This is the repulsive force on an electron. And, you know, basically it says for every proton there is an electron, right? So it says that when this force gets bigger than this force, the gas will be pushed out. When gravity is stronger than the radiation, the gas will fall in. So basically there is a limiting luminosity above which you cannot have accretion. But since the radiation is produced by accretion, the process shuts itself off. So you cannot exceed the Eddington luminosity, roughly speaking. And I say roughly because you can imagine geometries where the accretion takes place in a plane and the radiation escapes along the poles. But let's ignore that for now. And so the limiting luminosity, what will it be? It's called the Eddington luminosity. Let's put a subscript E here. It's related to gm over r squared times the mass of a proton. And the amazing thing is that r squared drops out, right? So basically the luminosity, the limiting luminosity has nothing to do with distance in the Newtonian limit. It just relates, it's 4 pi g times m times the mass of the proton divided by the Thomson cross-section times the speed of light. And it turns out to be 1.4, if you put in the numbers, 10 to the 38 ergs per second for a solar mass. For a black hole that has one solar mass, 10 to the 38 ergs. You work perhaps in watts, so I'll convert it to watts. There is a factor of 10 to the 7. So it's 10 to the 31 watts. Okay? Or 10 to the 38 ergs per second for a solar mass. And then if you have a 10 to the 9 solar mass black hole, then you multiply by 10 to the 9. So it's 10 to the 40 watts. Now the amazing thing is, when you look at quasars, these are accreting black holes, and you plot their luminosities versus mass, you find that, you know, there is this line of the Eddington luminosity where the luminosity is proportional to mass. You find that the data sits, most of the, you know, there are thousands of quasars, and most of them sit between 0.1 Eddington and Eddington, like in this range. You don't find anything above. So physics is respected by quasars. That's nice. It means that we understand something. But it, you know, as I said, you can in principle get geometries that would allow luminosities to exceed Eddington. But in most astrophysical cases, the Eddington luminosity is the limit, and it's just proportional to mass. So coming back to Andy's question, the mass dictates also how bright the black hole can be. Simply because radiation pushes the gas out if it's too bright. And then you don't get accretion, so then it's a self-limiting process. Okay, so you can attempt to go above Eddington, but then it shuts itself off. And one way by which you go above Eddington is if you have, for example, a star like the sun. Let's imagine the sun going near a black hole. So what will happen to the sun near Sagittarius A star? To figure this out, we have to see if the tidal force is stronger than the sun's self-gravity. So that now I go to a different calculation than we did here. So I'll erase this if it's okay with you.
Push it up.
Oh, I can push it out.
Yeah.
Oh, that's nice. Okay. So if we have the black hole, and now we have a star like the sun, let's say, star, and the star has a size r star, that's the radius of the star, and the distance, let's call it r again. So the star, the force that binds the star is gm over, let's call it r star squared. That's the radius of the star. That's the gravitational force acceleration on the surface of the star. But the question of whether we rip the star apart or not depends on the difference in force between the two ends of this star. So the star will be ripped apart if the force that binds it is smaller than the tidal force. Now, what is the tidal force? It's the gravitational force, but the variation of the gravitational force across the star. So it's the size of the star divided by the distance from the black hole, because that's the fraction of the variation in the gravitational force, times the gravitational force. So that's what we get as the condition for disruption. And this is called tidal disruption. So it boils down to a very simple condition. Let's call this the tidal disruption. Let's make this an equality sign and define the tidal disruption distance where stars get ripped apart. What will be the tidal disruption distance? It would be the mass of the black hole divided by the mass of the star to the 1/3 power times the radius of the star. Okay? And if for Sagittarius A star, we have 1,000,000 times the mass of the sun, so this is 100. 100 times the radius of the sun. The radius of the sun is 10 to the 11 centimeters. That's roughly 1 astronomical unit, or the distance between the Earth and the sun. So it's 10 to the 13 centimeters. And just for comparison, the Schwarzschild radius of Sagittarius A star is 10 to the 12 centimeters. So what that means is that if you bring the sun at a distance of 10 Schwarzschild radius from Sagittarius A star, it will get ripped apart. So we will see that. But if you take a much more massive black hole, the star will not get ripped apart. It will be swallowed whole. It will get into the horizon because the black hole mass density. So this is a condition on mass density. You see, the mass of the star divided by the radius cubed is the mass of the black hole divided by the distance cubed. So if you make the black hole very massive, it basically is very dilute. The density of the black hole is small and the star does not get disrupted. So big black holes like this one swallow stars whole. They just swallow a star and you don't see it anymore. But small black holes like 10 to the 6 solar masses like Sagittarius A star can disrupt the sun-like star. And the transition between the two regimes is around 10 to the 8 solar masses. Now, can anyone tell me why is the sun disrupted? And I said before that an astronaut will not care about coming to the horizon of a black hole. Yes?
The sun's a lot bigger than an astronaut. So
No, that's not. No, it's the density that matters, right? So in this condition here, what matters is the mass over the radius cubed, right? So the density of our body is very similar to the density of the sun, the mean density of the sun. It's about 1 gram per cubic centimeter. So, by the way, does anyone know? I asked my freshmen at the freshman seminar, I asked them, how much is the density of air lower than the density of the table? By what factor do you think? How much do you need to separate atoms? By how much relative to their own size so that you get air versus piece of wood? 10 times the size of an atom, right? So it's 1,000 times more dilute, right? The air is 1,000 times more dilute. I mean, even though it feels very different, it's only 1,000 times less dilute. So the distance between atoms is 10 times the size of an atom in air. Still, we can see through it. But at any event, the human body has roughly the mean density of the sun. So that's not the explanation. So how is it possible that an astronaut will feel nothing and the sun is getting torn apart? Good point. We are not bound by gravitation, right? Our body is not self-gravitating. If it were, then astronauts would be torn apart much more easily. That's a good point. Okay, so we learned two important things that appear in many contexts. This is an artist illustration of M87. It's not part of the press release in a month and a half, so don't take it too seriously. But it might not be very different, actually, when I come to think about it. Anyway, these are images we produced using a computer simulation of what the shadow might be like. So this was the very first paper that talked about M87 and made predictions about what you might see. And back then, again, people didn't care much about it. Now the difference is that there is this jet, that you're looking at the shadow of the black hole against the jet. And depending on what you assume about the physics of the jet, you can get different images. So let me skip over that and get to the issue of binaries, pairs of black holes. By the way, in astrophysics, this is an interesting lesson. You know that in real life, you can have a single object as a stable system. You can have two objects in a stable configuration, right? These are called marriages. But if you put a third body into the system, it becomes very often chaotic. And that's true of human life as well. Anyway, the same is true in three-body systems. They become chaotic dynamically. But when two galaxies come together, if there is a black hole at the center, you get a binary, a pair of black holes. Now, what happens usually is that each black hole sits at the center of the galaxy. And so it comes with this cloud of stars and gas. And so it's quite massive. And they spiral towards the center of the merger product. And you see here, these are real images from the universe where, you know, two galaxies came together and there are these tidal streams and the two black holes are coming together. And here are lots of images where you see two active galactic nuclei, actually. You see two bright spots when two galaxies come together and gas is fueling both of them.
And do we expect the two black holes to get in a bound orbit? Is that what you're saying?
Yeah, because, well, the two galaxies come together, by the way, because they are bound. Okay, the two galaxies.
Two galaxies.
And then the black holes are at the cores of those galaxies. And there is this phenomenon of dynamical friction where the gravitational interaction brings the cores of the two galaxies together. Now, we, by the way, have a sister galaxy to the Milky Way. It's called the Andromeda Galaxy. You can see it on this. I actually, first time I visited Australia, it was amazing. We went to Tasmania, which is a small island, and looked at the sky. And for the first time in my life, I saw the Milky Way in its full glory. And it illustrates, even though I wrote papers about the Milky Way before, I was struck by the fact that it really exists out there, you know, that. Because in particle physics, you talk about things that you never see, right? But in astronomy, the amazing thing is you can see what you're talking about. You know, that's a great perk. I encourage all of you to become astronomers.
The black holes are hard to see.
Well, not really. Well, first of all, even if they are naked, there is Hawking radiation, there is gravitational waves, right? So, but if you put gas around, you get a lot of fireworks. So anyway, you can see this from Tasmania. You can see the Andromeda Galaxy, which is a sister galaxy to the Milky Way. If we could see the dark matter halo of Andromeda, can anyone guess how big it would be on the sky? How big would the halo, the dark matter halo of Andromeda be on the sky? It would cover half of the sky because the two galaxies are touching each other right now, the halos. Unfortunately, we can't see the dark matter. But we are at the beginning of a merger with Andromeda. The Andromeda is falling towards us. Within 2 billion years, it will collide with the Milky Way. And in fact, you know, when I started astrophysics, I went to one of my colleagues who is now in an office close to mine named Lars Hernquist, and he was a postdoc at Princeton back then, and I said, you do simulations of mergers of galaxies. Why don't we do a simulation of the merger of the Milky Way with Andromeda? It's a simple thing. I just started astrophysics. I said, why don't we forecast the future, how the sky would look like in the future? And Lars said, yes, that's a great idea. I'll put it on my to-do list. And he kept putting it on his to-do list, but it was always number 10. And he never got to it. Then he left Princeton. And then he never got back to me. So at some point, he came back here, and I asked him if he's interested. He said it's still on the list. And then at some point, I decided to ask a postdoc, just like every Broderick, another postdoc, and I said, why don't we do this? He said, great, yes, that would be fantastic. Did the simulation. That was the first simulation, believe it or not, of the Milky Way with Andromeda. And we forecast. Now, why don't they care about that? Because it's in the future, so you cannot test it. Okay, as if we are very practical people, right? We are doing astronomy just because we are, building construction sites out of it. Obviously, we are doing academic works, and to me, it's as interesting to think about the future as it is about the past. I mean, who cares if we can't see it right now? I mean, it's something to figure out, what will happen in the future. And so we did this simulation, and actually we managed the merger. We mentioned the merger product many times in the paper and tried to abbreviate it into Milkomeda, the Milky Way and Andromeda. Then it became a name that other people use. At any event, we are eventually within 2 billion years will merge, and then the two black holes will come together. So everything we see on the sky will be next door, will happen. The sun will be kicked out. That's one of the outcomes of these simulations that we did. Anyway, we see those mergers. Here is an example of a binary black hole system so that is observed in X-rays a long time ago, actually, in 2002. And so there are many examples where we see two black holes. Like there are situations where we see two sources of jets. It's quite amazing. There are cases where we see a variation as a function of time of the brightness of a black hole because of the relativistic Doppler effect. So all of this is exciting. And then we wrote a theoretical paper some 7 years ago where we asked, is there a possibility for a triple system? If the two black holes don't come together and a third one comes in principle, you can have triples. And by the way, these systems will be visible in gravitational waves with LISA, very easily with the LISA observatory, currently scheduled for 2034, but perhaps it will start as early as 2028. You will have faculty positions at that point, but it will be very exciting.
Are there any regions where you have many black holes orbiting each other, like a halo of black holes?
Not that we know of. So the 3 was actually something that nobody else considered before, and you can imagine more than 3. Now, for stellar mass black holes, what happens is near the center of a galaxy, stellar mass black holes are 10 times more massive than a star. Okay, so just like dust particles in air, they segregate by gravity. They fall deeper in the potential well, and so this is called the mass segregation. And you expect stellar mass black holes to collect near the centers of galaxies. We haven't found evidence for them yet, but we expect there to be 20,000 stellar mass black holes within the innermost light year of the Milky Way. 20,000, 10,000 or so. And we also expect the same phenomena in clusters of stars, like globular clusters. Why is that important? Because LIGO not only detected the first event, you have to understand the psychology of LIGO for decades, and Andy probably remembers that. The people that worked on LIGO for decades thought we have to work really hard on forecasting what the signal would look like because our signal to noise would be barely, really weak. We won't be able to actually see the signal with our eyes. We will have to use software. And for that, we need templates. Now they open their eyes, LIGO eyes, to the sky. And within 2 weeks, boom, huge signal. Everyone can see it. No need for a template. Who cares about the template? OK, well, there is a template that fits it very nicely, but you can see the signal. How is that possible? Why did this happen? And then, of course, people would say, oh, yeah, obviously, but the psychology was very different before. I'm just telling you the truth, by the way. Everything that I tell you is the truth.
But without the template, we wouldn't have known what the signal was from, right?
No. What do you mean? No. The point is, crudely speaking, you don't need, if you look at the Physical Review Letters paper of the first event from LIGO, you don't need any sophisticated computer simulation. You can just look at the signal and infer some, the error bus will be bigger than if you were to put a template on top, but you can get some basic parameters of the binary. You can see the signal. You can see that it's a real event without doing any sophisticated template fitting. And the question is why? So whenever something is different than you expected, there must be a reason. Let me give you an example. 1952, there was a guy named Otto Struve that said, OK, we see Jupiter in the solar system at some distance from the sun. Let's imagine a situation where you take Jupiter and put it very close to the sun. So it orbits every few days around the sun. Why is that interesting to think about? Because then it will move the sun back and forth. So if we imagine it on another star, we can look for the motion of the star and infer the existence of such a Jupiter close in. So he suggested it in 1952. And nobody paid attention. Why? Because everyone said it makes no sense to put Jupiter close to the sun. Why? Because we look at the solar system, we see Jupiter far from the sun. And therefore, Jupiter cannot be close to the sun. And then, generations of, I'm not making a joke. I mean, this is the way astronomers think, and I suffer from it. Not that I think that way. I suffer from the fact that my colleagues think that way. And I can give you examples. Just check the news recently. Let's put it this way. Anyway, so for decades, and then there were some observers at some point, 3 decades later, some observers said, why don't we, we have now the instruments, we can detect stars moving back and forth if there is a Jupiter close to them. Why don't we do that? And there are these committees, time allocation committees, that decide about allocating telescope time. And they said, no, there cannot be a Jupiter next to a star. How many times can we tell you that? It reminds me that the church didn't want to look through a telescope when Galileo said, look, the Earth moves around the sun. Anyway, so it repeats. So people don't learn from history. That's the other thing that you realize. Anyway, so the time allocation committees of professional astronomers would not give time to people requesting to check if there are Jupiters next to stars. And then by some miracle, someone did it and found a Jupiter close to a star. And that opened up the whole field of exoplanets, which now has, thousands of exoplanets. And the first bunch of them were Jupiters close to stars that are called hot Jupiters. And now, of course, some theories say, oh, yeah, of course, we can explain that. But the reason I bring this up is there is hostility towards things that are very reasonable, that we didn't know about. And if you just say, no, let's, like an ostrich, let's put our head in the sand, you will never see them. And I don't know if there are examples in particle physics, but in astronomy there are examples.
Only astronomers.
Only astronomers. But at any event, with LIGO, okay, so here is so then, to explain the reason why hot Jupiters were not discovered, the reason for that is that astronomers are conservative. There is always a reason why something is unexpected. In the case of LIGO, why did LIGO see a signal so strong when we didn't expect it? The reason could be that these sources, well, we know that there are very massive black holes. The reason that the signal is so strong is you have 40 solar mass black holes in a pair. These are extremely rare. So how can you get two black holes, 40 solar mass, when each of them is so rare, put them together, and make this the most common source in the sky that LIGO would find? And the reason is that maybe what we are looking at are objects that are made in the center of clusters of stars. So the more massive black holes collect near the center, they find each other there, and they find a partner that is very massive. So all the 40 solar mass black holes segregate to the center and find their mate there and make these binaries that we didn't expect. So these are factories for making binary black holes of 40. So that's a natural explanation. Still not validated, but to me it sounds like the most plausible channel of making these very bright signals in gravitational waves. Anyway, one thing that can happen when you have systems like triples, as I said, they're unstable. So what happens is one member of the triple gets kicked out. Again, just like in the case of humans. But the speed here is sometimes thousands of kilometers per second.
What are the lines there?
Okay, so the lines are the distribution of, the density, the distribution of stars or density profile around the center.
Oh.
It's from a numerical simulation that we have done. Anyway, the point is that you can get black holes kicked at very high speeds as a result of triple systems. And there is another effect that can take place when two black holes come together. You can get gravitational wave recoil.
Is there a qualitative way of understanding why one would go off at a very high speed?
Yes, it's usually the lighter one that, you have to do a numerical experiment. It involves chaos. When you have three bodies, once you have more than two bodies, you can get chaos in the system. And then what happens is an orbit becomes unstable and just an object gets flung out. And it's very difficult to forecast that, but you can do it statistically speaking. Every time you run the simulation, because it's chaotic, you can get a different outcome, even from the same initial conditions due to numerical noise. But statistically speaking, you can figure out how frequently things get ejected. And another reason to get a black hole ejected is if two black holes come together and then gravitational waves are not emitted in the same, at the same intensity in all directions. You have a preferred direction, which is basically when the two black holes get to the ISCO, the innermost stable circular orbit, they plunge into each other, and then gravitational waves are emitted in a preferred direction, and that gives a kick to the system in the opposite direction, momentum conservation. So if you emit gravitational waves in one direction, you get a kick in the opposite direction. And the speed could be tens to thousands of kilometers per second. So at the end, you can get black holes kicked out of the centers of galaxies for two reasons that I mentioned. And we see evidence for such black holes that are moving away from the centers of galaxies. And by the way, it could be that there are lots of floating black holes due to this process in the Milky Way halo. And I will not get into the details.
So the idea that we have observational evidence, there's no such thing.
Oh, yeah.
It's a theoretical.
Observational evidence, and the evidence comes, again, I wrote several papers on this a decade ago, but there are two things you can measure. One thing is, if there is gas around the black hole, it can emit spectral lines, and then you can measure an offset in the redshift associated with the black hole relative to the host galaxy. Okay, so you can see that there is an offset due to the motion. That's the spectroscopic way to find it. But then you can also see a spatial offset in the sense that there is an active black hole that is displaced from the center of the galaxy. These are the two ways.
And how do we know it's a black hole?
Well, we see a very bright source radiating at a very high luminosity near the Eddington limit, or we measure the width of the spectral line and see that it's very broad. That usually you don't see that in stellar systems. So another interesting thing that you can get is when two black holes make a binary, they can kick out stars, sort of like a slingshot. This is a gravitational slingshot where you can shoot off stars at speeds that could reach the speed of light. So, travel agencies can sell tickets on planets near these stars that can take you close to the speed of light. And we actually calculated and found that there should be a sea of stars filling up the universe. I mean, we tend to think just about photons, radiation, but there is also a sea of stars in the intergalactic in the medium between galaxies that move all the way up to the speed of light. They were ejected from black hole binaries. And we calculated the abundance of those stars, but we couldn't figure out a simple way of observing them, but because they are quite rare, and the density is small. But you can do cosmology with them.
Theoretically, it's predicted that the density would be small.
Well, we predicted how many. We calculated how many mergers there should be, per unit volume in the universe, and then multiplied by the number of stars ejected in each merger, and just calculated how many you should expect during the age of the universe. And there should be a sea of those stars. Now, in principle, when we do cosmology, we use photons, and they move at the speed of light. So you have the notion of a distance, which is associated with a redshift. Based on a particle, the messenger moves at the speed of light. The same is true for gravitational waves. They move at the speed of light. But if you have a particle with a mass that doesn't move at the speed of light, you can do miracles in cosmology, because now the time delay for the time that it takes this thing to arrive to us from the source is longer than it takes light. And you can see the source at different times, depending on what's the speed of this messenger. And by the way, if the neutrino we know the neutrino should have a mass, then in principle at low enough energies you can do that, but you cannot detect low energy neutrinos from cosmological distance. But it's just, we are used to cosmology with massless particles. If we had cosmology with massive particles, it would be much more fun, actually. Because then as a function of energy, you would get different time delays. So that's just a comment. And we actually worked out how cosmology would be different with these stars if you were to detect them. And finally, I wanted to mention the tidal disruption of stars, and that boils down to what we discussed before. And if you ask what is the rate by which stars are being consumed by black holes, it's roughly once every 100,000 years for a Milky Way galaxy. And as I said before, black holes with a mass above 10 to the 8 solar masses swallow the star whole. This is simply because the tidal radius that you calculate from this expression is smaller than the Schwarzschild radius.
Sorry, I'm not understanding this.
Yes.
What happens every million years?
Every 10 to the 5 years, a star like the sun wanders by chance close enough to the black hole to be ripped apart.
Does Sagittarius A star?
Or any other galaxy. So, if you go back to when the dinosaurs were on Earth, they must have seen a star being disrupted. But we didn't see it because we came later. So every 100,000 years, if you wait long enough, you will see a star being ripped. Now, the amazing thing is, when this happens, you can ask, okay, suppose you take the star, what happens? So you basically make a stream of gas out of it because you rip it apart. This is called spaghettization. I don't remember how to spell spaghetti, but never mind. You basically make a spaghetti out of a star. And you make a stream of gas that is swirling around the black hole and eventually accretes onto the black hole. Okay? And it's very thin, this stream of gas. But you can estimate what is the feeding rate of the black hole as a result of that. And you get how much mass is falling into the black hole, dm dt, which is called the accretion rate. And by the way, if you multiply this by c squared and multiply by a radiative efficiency, so this is the efficiency of converting rest mass to radiation, then you get the luminosity coming from the black hole. So you can ask, what is the luminosity that you get from the disruption of a star? And it turns out that it's 100 times Eddington. You get a mass infall rate that exceeds the Eddington limit by a factor of 100 or more. But that doesn't mean that you get radiation above the Eddington limit, because what it means is that you can easily liberate enough energy to basically disperse the gas. But there is a huge amount of feeding that comes with the disruption of a star. 100 times Eddington. So if there was a star disrupted by Sagittarius A star, then it would become extremely bright. And by the way, we wouldn't be able to use the Event Horizon Telescope to see through the gas because it will be opaque. And by the way, the amount of X-rays that we get from Sagittarius A star in the case of a disruption of a star is more than the amount of X-rays that we get from the sun right now. So it would be very visible, such an event. And actually I said here, super Eddington feeding rate. And that you can get roughly by a fraction of the mass of the star. By the way, the star, you can cut the star into two halves, and half of the star remains bound, and another half is flying out, becoming unbound, so to speak. That's roughly speaking what happens. Here is the expression for the tidal radius that I derived for you over there. And you can get all kinds of relativistic effects, lens steering. I will not get into that. There was potential evidence for that, actually, in some data. And finally, primordial black holes. That's the place where we started. And as I said, it's density enhancements of order unity on the scale of the universe, the scale of the horizon, the Hubble size, that can happen early on in the universe. And that could be the dark matter candidate. And if the mass is bigger than an asteroid, then such a black hole would survive for the age of the universe. And as I said, the Schwarzschild radius is roughly the size of a proton for such a mass. So if it goes through a proton, it can break it by the tide, in principle. But it doesn't do much to the Earth except excite the seismic waves. So could the dark matter be primordial black hole? So now I'll just mention very briefly two things. It's based on two papers that we wrote about 5-6 years ago. Two ways of limiting the amount of mass in the universe in the form of these black holes. One of them has to do with the process of black hole bombs. I don't know if anyone discussed it here. No? Okay, so suppose you have a black hole and you put mirrors around it. So then there was this paper by Press and Tokolsky in 1972, long before you were born, which said that such a system will become unstable, that if you put this spherical mirror at the right distance from the black hole, there would be modes that would be amplified, just like in a laser, and eventually, I mean, in the case of a spinning black hole, eventually there would be an explosion. Basically, you will extract energy from the spin and create a bomb. Now, this is different from Hawking radiation, where he also thought about it being like a bomb where black hole evaporates. Here, it's not Hawking evaporation. It's just surrounding a black hole with a mirror. Some 6 years ago, I thought, oh, well, actually, in the universe, if you have primordial black holes, there aren't really mirrors, but something very similar to a mirror. There is a plasma, which is ionized gas in the early universe, and a plasma has a dispersion relation. When a photon, a particle of light, goes through a plasma, the energy squared is equal to a mass squared plus momentum squared. So a photon acquires a mass in a plasma. This is the dispersion relation. And by the way, that's why mirrors reflect, because the plasma, when the frequency of the radiation is less than the plasma frequency, you cannot get propagation. You get an imaginary K vector. Okay? And so that means that the wave damps and cannot get through the medium. It reflects, right? That's what a mirror is all about. You have silver or aluminum, whatever you have on the other side of the glass, okay? And there are free electrons in that metal. And the free electrons have a density which gives you a plasma frequency above the frequency of light. So that's why you see your face, because visible light cannot propagate into that metal. It has a too high density of electrons. So a mirror is, you can realize a mirror by having a plasma with a plasma frequency above the frequency of the radiation, okay? And this is equivalent to having a particle with a mass that is above its energy, so it can't really go there. A tachyon. Now, in the early universe, the proton, the plasma frequency was a function of time. So the universe was denser at earlier times, and then it expanded. And so the photon mass changes with time. So if you imagine a primordial black hole surrounded by a plasma, there was a cosmic time when the plasma frequency would be just right to reflect these modes that were talked about by Press and Tokolsky. So the idea is that if you have spinning black holes, you can get these bombs around them in the early universe due to the reflection by the plasma. So that was a paper that we wrote, and we were able to put limits on, from this phenomena of superradiance on primordial black holes with a mass between 10 to the minus 8, the mass of the sun, which is less than the mass of the moon, basically. Of order the mass of the moon to the mass of the sun. This is the line from superradiance. But there were previous constraints already. And this is here, this dashed line here, is having all the dark matter made of those black holes. So what we can say is that very small fraction of the dark matter is allowed to be in the form of these black holes, because otherwise what would happen as a result of these bombs, you would put energy into the cosmic microwave background that we don't see. The microwave background has a Planck spectrum, black body spectrum, and if there were these bombs, they would distort that spectrum. So just from the limits on the microwave background, we get this limit on how many such black holes are allowed to exist.
But with J over M squared of order 1.
Yes, exactly. So the point of the matter is that if you make them in the universe, then you really need to fine-tune the conditions such that you will have no spin, because typically you will have inhomogeneity. So that was the argument. And then another possibility to constrain primordial black holes is if you have neutron stars. By the way, a neutron star has roughly the mass of the sun and the size of Boston. Okay, so you take the sun, compress it to the size of Boston. What density do you get? Nuclear density. So a neutron star is what happens when the core of a star, the star is not too massive, so the core of the star, instead of making a black hole, makes an object that looks like a giant nucleus, just like a nucleus of an atom, except it has the mass of the sun. And that's called the neutron star. And actually Landau thought, neutrons were discovered, why not make a star out of them? And then, again, in the spirit of, I'm sure that if there were astronomers at that time, they would dismiss it and say that's nonsense. Probably there were. Anyway, we know that such objects exist. They are called neutron stars, and they exist now. If a black hole, a primordial black hole, was swallowed by a neutron star, and this black hole would sink to the center of the neutron star, it could eat it up. And if every neutron star would have had, during the age of the universe, one such black hole being swallowed, you would lose all the neutron stars. We wouldn't have any. So you can use that to put a limit on the abundance of primordial black holes. Yes?
Why did we call the previous phenomenon, like with the plasma mirror around a black hole, why do we call that superradiance?
It is superradiance.
Like in the same way that like nonlinear atomic optics systems.
Yes,
produce
it is called superradiance.
See,
Yes.
that's weird to me because I usually associate superradiance as like a quantum phenomenon.
It is no, it's a classical. No, so it could be, okay, so a laser amplifies coherently radiation. Quantum mechanically, you can think of it as a process by which you have photons occupying a particular state, let's say in frequency, and that enhances through the Bose-Einstein statistics the chance of another photon occupying the same state. So when you have atoms decaying, they would decay more rapidly now that there are already photons in that state because of the factor of 1 plus the occupation number. So that's stimulated emission. Okay, and so that's one way to think of it. But another way is classically, because when you have a lot of photons occupying the same state, they behave as a classical field, right? Because a lot of them means that there is not much uncertainty in the system, because you have a lot of participants with the same properties, and then square root of the number of participants means that you really don't have much variance, and the system behaves as a classical system, okay? And that's called an electromagnetic wave in classical electrodynamics. That's the reason that Maxwell's equations make sense, even though quantum mechanics was developed afterwards. And so at high occupation number, you get classical, okay? And what that means is that you should be able to describe a laser classically also, right? And so how do you understand that? You have an electromagnetic wave, and there are these, you can think of them just like systems of springs, like resonators, small resonators that have a characteristic frequency. You call them atoms. They have a characteristic frequency that they can radiate. And when you have an electromagnetic wave passing through systems of resonators that have a particular you can get a resonance between the two, and as a result extract energy from the resonators. You see that you can do the same experiment in acoustics also so that is the classical analog of stimulated emission. And the same holds for the black hole case here, that basically you can think of it as an electromagnetic wave that is in resonance with the cavity, and as a result, as it bounces back and forth, every time it bounces, it extracts spin energy from the spinning black hole. So you can think of the spinning black hole as having a characteristic frequency, just like an atom. And every time you bounce off it, just like an electromagnetic wave interacting with atoms, you gain some energy. And if it's constructive interference kind of situation where you keep adding more and more energy to the electromagnetic wave, and you end up with a catastrophe, or in the case of a laser with exponential gain. So it's exactly the same situation. And actually, Zeldovich and Novik, Zeldovich had a group of people in Russia that worked on superradiance and the extraction of energy from spinning black holes back in the early 70s, and he kicked himself for not finding Hawking radiation, because you can derive in principle Hawking radiation if you realize the analogy with systems of atoms, and after you derive superradiance for black holes, as Zeldovich did, he could have translated that to the quantum language of Hawking radiation, but he didn't. So, but after the fact, he realized. So superradiance was derived classically before Hawking derived his results. Anyway, so we pretty much got to our time limit, and I also got to the end of my discussion. I'll be glad to answer any urgent remaining question.
If there are no urgent questions, let's thank God.
Thank you.
Yeah.
Thanks. Thanks for solving the problem. That was really crucial.
I don't know why the other box wasn't working. Just ended up being switching boxes.
Great job. Just sorry.
Thank you.
Yeah.
Thank you.
And I enjoyed reading these papers.
Now I can tell you what. I can tell you what happened to me today. Other than that, if you want to hear.
Oh, sure, yeah.
But maybe there was a question. Did you want to ask?
It wasn't quite urgent, so is it okay if I ask?
Yeah.
The thing is that, so the reason that there's no primordial, the reason that we say that all of the dark matter is not made out of primordial black hole is that